Okay, so some examples in section 7.4, integration by partial fractions. We're going to do this. We got integral of dx over 16x squared minus 1. Regular substitution doesn't work because if you let u equal 16x squared minus 1, du would equal like 32x dx. There's no x up here to get rid of. So regular substitution doesn't work. So we want to try and do some other methods. I think this is 16x to the x to the fourth. I think I read it wrong. So anyway, let's factor this out. If it's not, it's like number 15. But anyway, we can factor this out. So we can say 1 over 16x to the fourth minus 1. That's a difference of two squares, right? So we want to factor this out. And so that would factor as 4x squared minus 1 times 4x squared plus 1. And of course, the sum of two squares doesn't factor, right? But the difference of two squares does. So we got to remember our factoring rules. So this is also 1 over 2x plus 1 times 2x minus 1. The conjugates of the square roots times 4x squared plus 1. So we can basically break this fraction down into factored form like this. So what we really want to do is we want to write this as being equivalent to something over 2x plus 1, something over plus something over 2x minus 1, plus something over 4x squared plus 1. And of course, if you remember, what we talked about before, whatever the degree of the denominator is, what do we have to have for the numerator? What kind of degree? Like if this is first degree, this has to be just a constant, right? So this is just an A. So this would just be a constant, which would be a B. But if I'm second degree, what do I got to have up here? One less degree. So it's first degree. So that would be like CX plus D. So I got constants A, B, C, and D that I need to figure out what they are. And once again, what does that equal? That equals this right here. So what I could do is I could multiply both sides by the denominator, right? And if I do that and multiply that through, what do I get? I'm going to get 1 on the left for this part, multiplying through by that denominator. And then on the right side, the 2x plus 1s are going to cancel out. So I'm going to get A times 2x plus 1. Excuse me, that one cancels. So what's left is 2x minus 1 times 4x squared plus 1. And then plus, when I multiply that denominator through by B, the middle one cancels. And I'm going to have B times the quantity 2x plus 1 times 4x squared plus 1. And then plus CX plus D times, now the 4x squared plus 1 cancels, so it's going to be times 2x plus 1 times 2x minus 1. Okay, everybody good with that on multiplying through by the denominator, clearing the denominators out of there? And then really what I got to do is I got to solve for A, B, C, and D on this so that I can figure out how to rewrite this antiderivative up here. Okay, so a couple different ways to do it. First of all, we have 4 equations, 4 unknowns. I don't really want to do it that way. I'm going to try and use that trick that we talked about. So what happens if we let, what would make this one 0? If we let x equal what? What makes 2x minus 1 0? 1/2. So if we let x equal 1/2, let's see what we get. We're going to get 1 on the left side, and on the right side, this one is 0, and the last one is 0. So I'm going to get, the middle one is not 0. So anyway, so b times what? If x is 1/2, 2x plus 1 would be 1 plus 1, so b times 2. And then 1/2 squared is 1/4 times 4 is 1 plus 1 is 2. So basically we get 4b equals 1, right? So what does that say B equals? 1/4, right? Everybody good with that? So it's kind of a cheating way to come up with B on there. Okay, so we have that. Then what else could I let X equal? Let me erase this up here. What's another easy one that's going to get rid of something in the denominator? What about this? What about this one? 2x plus 1. What could I plug in there to get 0? -1/2. So if x equals -1/2, I still have my 1 on the left side. And on the right side, these two both are equal to 0. So I just have my a term left. So a times, and then -1/2 times 2 is -1, minus 1 is -2. And then -1/2 squared is 1/4. So that'd be 1 plus 1 is 2. So that says that 1 equals -4a. So that a equals -1/4. So we get that. So we know that we can split this integral. We can split this up into the definite integral of a was -1/4, right? Whoops, that's blue. Remember, I don't like solving for b first because I always like to throw that in first, so don't do that. Anyway, I'm going to pull that 1/4 out, or excuse me, the -1/4 out on top. And it's going to be the integral of 1 over 2x. Which one was first? 2x plus 1. I erased that part. 2x plus 1, right? When I split it up into a over, was it 2x plus 1? Okay, so the a is -1/4, but instead of writing it on top, I'm just pulling that a out in front. Okay. Anyway, and then I've got plus b over 2x minus 1 is what we had. B is 1/4. I'm going to pull that out front. So it's going to be the integral of 1 over 2x minus 1 dx. And then plus, then we had cx plus d over the other stuff. Okay, so what we need to do now is we can pick a different number. So what's an easy number to pick? How are you going to solve for C and D? So like, in other words, what can I plug in for x to make 4x squared plus 1 equal to 0? Anything? If you know the base graph shift, x squared, we squeeze it, then we move it up. There's nothing that touches or crosses the x-axis, right? So there is no value that makes that equal 0. 4x squared is going to be greater than or equal to 0, and then you add 1, it's going to be strictly greater than 0. So there is no 0 that we can get by plugging in an x. So what's an easy number to plug in? It might give us a fairly easy equation. I mean, you can plug in anything. Do you want to plug in pi over the square root of 2? Or what do you want to plug in? About 0. 0 makes some pretty easy math, right? So if x equals 0, if I let x equal 0, let's just see what we get. Once again, on the left side, I get 1, right? Nothing changes. On the right side, I'm going to get a, and I'm just going to put it as a because I already know what a is. But I'm not, I'll just fill that in next. But a times, and then it's just -1 times +1, right? Because 4x squared is 0 plus 1. And then plus b times 1 times 1. And then plus cx plus d, quantity, times, and plugging in 0 for 2x plus 1, I just get 1. Plugging in 0 for 2x minus 1, I get -1. So does everybody agree that's what I get? Okay. So if I do that, let's just make this easier. So So I've got 1 equals, this is minus 1 times a, or minus a. A is minus a fourth, so that's plus a fourth, right? The opposite of minus a fourth. And then plus b, b was a fourth, so plus a fourth. And then plus, and this is negative 1 times c minus d, or excuse me, c plus d. So it's the opposite of c plus d. So it's going to be minus cx minus d. I'm just going to distribute that minus sign. Okay, so doing this, 1/4 plus 1/4 is a half. Subtract a half from both sides. And I'm going to get 1/2 equals minus cx minus d. I don't like the minuses on the constants. So do you guys care if I put the minus on the other side? Multiply both sides by -1. Watch how I do this. That's pretty cool, right? Okay, now the question is, what's c and d? Can you figure that out from this equation? Yep, we can. How would we figure it out? And I know what you're thinking. You're like, well, that's 2 unknowns. It's only 1 equation. How can you do that? Well, magic. What I can do is I can rewrite the left side. So basically, what kind of number, or what kind of term is the left side? Is it an x term or a constant? It's just a constant term. Which one of these is just a constant term, the c or the d? D. So the cx is an x term, right? So basically, if I rewrite this as cx plus d equals so many x's plus a constant, how many x's do we have on the left side? Do you see any? No, 0 x's. So it's 0x plus a -1/2, right? So could I rewrite it like that? I'm just rewriting the -1/2 to look like cx plus d. So what does that tell you c is? What's c equal? 0. It's the constant term on the x. And what's d equal? -1/2. Everybody see that? So I'm trying to give you the easy way that avoids you writing 4 equations, 4 unknowns, but I do teach a course called Finite Math, where we use matrix theory to solve linear algebra equations that either 3 equations, 3 unknowns, 2 equations, 2 unknowns, could do 4 equations, 4 unknowns. It takes a while. This is much easier because all we care about is how can I rewrite this problem right here in terms of a over 2x plus 1 plus b over 2x minus 1 plus cx plus d over 4x squared plus 1. So the last one I get is, what was d? Cx plus d is 0x plus -1/2. So in other words, it's -1/2. I'm going to pull that out front. So plus a -1/2 times the antiderivative of 1 over 4x squared plus 1 dx. Okay, so really, this is how I'm rewriting this antiderivative. I'm using partial fractions to rewrite it into a sum of 3 antiderivatives. Does that make sense? Okay, perfect. And then hopefully, these are in a form that I can handle what that antiderivative is. And this is why we did chapter 4 and 5 stuff, and earlier in 7 if needed. But anyway, so let's do this. So what about the first? Let's just do the blue one first. So we'll do it in pieces. We've got 2x plus 1. 1 over that. Well, what do you want to do? It'd be a lot easier if that was 1 over u, right? So we're going to let u equal, so this is substitution of section 4.2, but du equals 2 dx, right? Du over 2, right? So this ends up being equivalent to, once again, I'm doing all of the blue one. So this is equivalent to -1/4 times 1/2. So pull that 1/2 out front as well. And then I'm going to have du. And then it's 1 over u. What's the integral of 1 over u? Integral of 1 over u du. Natural log of the absolute value of u, right? Now I'm not going to put the plus c on there yet. But anyway, the coefficients multiply together to get minus 1/8. So it's going to be minus 1/8 natural log, and then I back substitute to what my u was here. It's natural log of the absolute value of 2x plus 1. And then plus some constant. But does everybody agree that the first piece is minus 1/8 natural log of 2x plus 1? Awesome. So then guess what? I can do it with the second one. Now the second one I'm going to do a lot quicker. I'm going to do this in my head, and I'm going to talk through how I think about it. So I could do the exact same thing I just did, except let w equal 2x minus 1. So the reality of dw would be 1/2. So this would be 1/8, the integral of 1 over w dw. But anyway, so just kind of going, it's going to be, if I did it in my head and I didn't do substitution, I might say, well, it's 1/4, and then 1 over that, that's natural log of the absolute value of 2x minus 1. Now, if I take the derivative of the natural log of the absolute value of 2x minus 1, I get 1 over, right? So I get 1 over 2x minus 1, which I have in the denominator, but chain rule says I also have to do what? Times the derivative of what's inside, which is 2. So I would get a 2 if I take this a&I derivative, or excuse me, if I take the derivative of the natural log of 2x minus 1, absolute value. I'd get a 2. I don't want that 2. So what do I have to also do? Times 1/2, right? To undo that 2 that I don't want because I don't have it up here. So what does that become? Then it's going to be plus 1/8 natural log of the absolute value of 2x minus 1. This is going to be that part, right? And now for the hard part is trying to come up with the a&I derivative of the last one. So I'm going to come over here. And so I've got minus 1/2. I'm going to rewrite it. Minus 1/2. Hopefully you can see that on there. Minus 1/2. Anybody remember what we got to use? What kind of functions? What that looks like? Could I write that as something squared plus 1? Could I write 4x squared as 2x quantity squared plus 1, or 1 squared really, but dx? Anybody remember what kind of functions that would be? I'll give you a hint. Inverse trig is one of the nice ones. It has to do with arctangent. So it's minus 1/2 times whatever that is. But it's the only thing you got to remember is that 1 over, so we got ax, is it 1 over a or not? I think with arctangent, anybody know off the top of your head? I know we got arctangent of 2x, right? So if we don't know where to look it up, go back up, look at your arctangent antiderivatives, or look on that sheet of antiderivatives, or front and back flap sheet I gave you. So it is, let's see. So it's the arctangent, but it'd be u over a. So 1 over a, u over a. So the a is 1, so that doesn't matter. But if I take the derivative of this, derivative of arctangent, basically what I got to do is I got to let, what would I do here? If I use substitution, I would let z equal 2x, right? And what's dz equal? 2dx. So dz over 2 is dx. So I would get a 1/2. out in front, and then this would be 1 over z squared plus 1 dz, right? So minus 1/2 would still be out there, but then what would I have to do? I'd have to have it times 1/2, right? And then this is the 1 over a. So the a squared is just 1. And so this is 1 over a, but 1 over 1 doesn't change. And then arctangent of z over 1. So arctangent z, and then z back substituted is 2x. All right, so anyway, coming back here, long story short, this is minus 1/4 arctangent of 2x. And then, of course, I need a plus c. So that's that one. And then a plus c. So the whole thing right here is the antiderivative using integration by partial fractions. So that's either 15 or one like number 15.